So the next lecture in the energy momentum unit is on conservation of energy, section 4.5 from your textbook. And I'd like you to copy down what's in green there. This is the law of conservation of energy. It's a simple statement. Energy is neither created nor destroyed. It can only change form. And you may have seen this in chemistry if you've taken a chemistry course, but the basic idea is that whenever we have a what appears to be a loss of energy, it's actually a change in energy from one type to another. So an object that is cooling is losing the thermal energy that it has, but there's a gain of thermal energy in the atmosphere that it is within. In a car that's traveling very fast that has a collision, it has a lot of kinetic energy, but after the collision, it may have deformed whatever it hit. There would have been sound. There could have been light from an explosion. That is another example of the law of conservation of energy. The general idea is that the amount of energy is finite, and what we observe, a change of energy, what we're observing is energy moving from one form to another, but we're not observing any loss of energy. There's no net loss of energy. And an example of this, we're going to look at a 65 kilogram diver who does a handstand dive from a 10-meter high diving platform into the water. So this diver is 10 meters above, and they are going to dive into the water. So these three images basically summarize the entire situation. So as you can see, while the driver's gravitational potential energy is transformed into kinetic energy throughout the dive, his total mechanical energy does not change. It is conserved. You'll remember from grade 11, mechanical energy is the sum of the gravitational and kinetic energies. So at the top of the dive, the gravitational potential energy is Eg, which is mgh. So m is, in this case, 65. I'll do this little calculation. 65 times g, which is 9.8, times h, which is 10. So 6,400 joules, or 6.4 kilojoules. He's not moving. Kinetic energy is 0. At the halfway point of the dive, his gravitational potential energy, he was 65, is 9.8 times 5, so it's 3.2 kilojoules. His kinetic energy would be 3.2 as well. And we can actually calculate how fast he's moving at that point. Because he's accelerating, he's going to be going faster. At the last point, Eg is going to be 0 because his m, 65, times g, which is 9.8, times the height, which is 0, but his kinetic energy is equal to what his potential energy was before he started the dive. At every point in time, his mechanical energy is the same. It's 6.4 kilojoules. So in the first situation, Eg is 6.4, Ek is 0, the sum is 6.4. At the exact midpoint, Eg equals Eg equals Ek. So that is 3.2 plus 3.2, which is 6.4. And the last point, his kinetic energy is 6.4. His gravitational potential energy is 0, but his mechanical energy is still 6.4. So the law of conservation of energy, please copy this down. Energy is neither created nor destroyed. When energy changes from one form to another, no energy is lost. The energy total at the start is equal to the energy total during, which is equal to the energy total at the end. And there's in that note, when we're involving only gravitational potential energy and kinetic energy, it's EGI plus EKI equals EGF plus EKF. But sometimes we'll add other types of energy as well, so that is not the only equation you'll need to know for the law of conservation of energy. So here's a situation. We have a skier gliding along with a speed of 2.0 meters per second at the top of a ski hill that is 40 meters high. The skier then begins to slide down the icy hill, which we're going to consider to be frictionless. What is the skier's speed at a height of 25 meters? And I'll show you how to calculate this. Okay, so this skier, the height of the skier initially is 40 meters. The skier's speed is 2.0 meters per second. And it says that we have to find the speed of the skier when the height is 25. So this is our VI. Our VF is the unknown that we have to solve for. So we know that our EGI plus our EKI is equal to our, actually I'll do it this way, the change in energy before, or the total energy before is equal to the total energy after. So EGI plus EKI is equal to EGF plus EKF. EGI is mghi. EKI is 1/2 mv squared, or vi squared. This EGF is mghf, and EKF is 1/2 mvf squared. Now we have an m in each of these. Our m is unknown in this case. But because there's an m here, 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 and here, the m is going to divide out. So this shows that our change in energy in this case is independent of the mass of the skier. So let's rearrange to solve for VF squared. So dividing both sides by m allows me to eliminate this m. And I can then, I'll just do it this way and show you, make our steps a little bit more slower, but that's okay. Now I need to get the VF squared on its own. So I'll swap these two sides and I'll write mVF squared over 2 equals GHI minus GHF plus VI squared over 2. Multiply 2 by everything here and divide, oh sorry, I should have stopped writing that m back here. This m is gone. So multiply everything by 2 and find the square root. I have the square root of 2g hi minus hf plus vi squared. So it's best to do physics problems by finding your equation and substituting everything in at once. This prevents you from the temptation of using an intermediate value that is rounded. You should always be using exact values when you're getting to your solutions and only round your final solution at the end. So 2 times 9.8, hi is 40, minus hf, which is 25, and vi, which is 2 squared, 2.0, but I'll write it as 2. So putting this into the calculator gives me 2 times 9.8 times, that's going to be 15. 40 minus 25 is 15, plus 2 squared, which is going to be 4. 298, and I find the square root of that. I get 17.26 meters per second, and I'm going to write that as, rounding for my significant digits, as just a 17 meters per second. On the next slide, you'll see that this problem then asks, at what height will the skier have a speed of 10 meters per second? So we have to go back to this equation. And we're looking at what time will his VF be 10? So at what height will his VF be 10? So in this case, we're looking for the HF. So I'm going to take this equation here and rearrange it. And I'll do this below here. So I'm rearranging it for HF. So I'm going to have GHF equals, that's going to be GHI plus 1/2 VI squared minus 1/2 VF squared. So HF is going to be HI plus VI squared over 2G minus VF squared over 2G. So I've just rearranged that. And then I'm going to substitute all my values in. HI was 40. VI is 2. G is 9.8. VF is 10. So this, putting all of this into my calculator at once, gives me 40 plus 2 times 2 divided by 2 divided by 9.8 minus 10 squared divided by 2 divided by 9.8 equals 35.102, which is equal to, after significant digits, 35 meters. So that's my solution to those two practice problems. So this next problem says that we have a roller coaster and we need the speed to be 10 meters per second at the top of that loop, which is 16 meters above the ground level. So in order for that to happen, what's our minimum height have to be? What must our minimum height be? So in this case, what we can do is we can find out, let me just switch over here, our minimum height is related to our change in energy. So our energy before, let's assume that the card is not moving at the top of that height, that HI, because this is our minimum height. So if our VI is 0 meters per second and our HI is our unknown, we know that our VF, our HF is 16 meters, and our VF was, I think it's at, what was it, 10? Let me just check here. Yes, 10 meters per second. So this must be 10 meters per second. So what we'll do is our EGI plus our EKI is equal to our EGF plus our EKF. Our EGI is going to be 0. Sorry, I should say our EKI is going to be 0. Our EGI is not 0. Our EGI is MG HI, and that must equal M 1/2 VF squared, and sorry, I wrote that over here, and MG HF. So here I can divide everything by M to simplify that. I need to solve for HI, so HI is equal to VF squared over 2G, and that plus HF. Substituting in, I end up with 10 squared over 2 times 9.8 plus my HF, which is 16. And in the calculator, this becomes 100, which is 10 squared divided by 2 divided by 9.8 plus 16. My height, 21.1 or 21 meters, my minimum height. So further on with this this concept of conservation of energy, it applies to any system of particles that is isolated from outside influences. So any group of objects can be defined as a system of particles. Now in the case we have here, we have an open system of looks like potatoes that are boiling on a pot. We have a closed system where the potatoes themselves, or the steam from the potatoes, doesn't leave the system. And we have an isolated system where the steam that would be leaving the potatoes in the open system stays within the system. It's isolated. So our open system, we have energy that can leave the system. The closed system, we have energy that stays within the system, but the atmosphere could still have an effect. And the isolated system, the atmosphere is included. So those are that's our law of conservation of energy has to be looked at in those three kind of types of systems. So in the open system, both matter and energy can be exchanged with their surroundings. But matter does not enter or leave a closed system, but energy can enter or leave. And in the isolated system, matter or energy can neither enter nor leave the isolated system. So this slide here just kind of explains what I said earlier. You can read this on your own, but it further explains the open, closed, and isolated system. And this slide here, I'd like you to copy this down. It says physicists sometimes refer to an isolated system as a closed system to contrast it with an open system. But this summarizes how matter or energy can be exchanged in the three different types of systems. So in an open system, matter and energy can be exchanged. In a closed system, only the energy can be exchanged. In an isolated system, sometimes called a closed system in physics, neither matter nor energy can be exchanged.